Magnetic effects of electric current. Does the electric current carrying wire behaves like a magnet? We know that an electric current carrying wire behaves like a magnet. Let us perform the following activity to reinforce it. Take a straight thick copper wire and place it between the points X and Y in an electric circuit as shown. The wire XY is kept perpendicular to the plane of paper. Horizontally place a small compass near to this copper wire. See the position of its needle. Pass the current through the circuit by inserting the key into the plug. Observe the change in the position of the compass needle. We see that the needle is deflected. What does it mean? It means that the electric current through the copper wire has produced a magnetic effect. Thus we can say that electricity and magnetism are linked to each other. Magnetic field and field lines. Let us explain with the help of an activity. Take a white sheet paper on a drawing board using some adhesive material. Place a bar magnet in the center of it. Sprinkle some iron fillings uniformly around the bar magnet and observe. You will observe that the iron fillings experience a force. The force exerted makes iron fillings to arrange in a pattern. The region surrounding the magnet in which the force of the magnet can be detected is said to have a magnetic field. The lines along which the iron fillings align themselves represents the magnetic field lines. Let us explain with the help of another activity. Take a small compass and a bar magnet. Place the magnet on a sheet of white paper fixed on a drawing board. Mark the boundary of the magnet. Place the compass near the north pole of the magnet. How does it behave? The south pole of the needle points towards the north pole of the magnet. The north pole of the compass is directed away from the north pole of the magnet. Mark the position of the two ends of the needle. Now move the needle to a new position such that its south pole occupies the position previously occupied by its north pole. In this way, proceed step by step till you reach the south pole of the magnet. Join the points marked on the paper by a smooth curve. This curve represents a field line. Repeat the above procedure and draw as many lines as you can. You will get a beautiful pattern as shown here. From this activity we conclude that magnetic field lines emerge at the north pole and merge at the south pole. The magnetic field lines are closer at the poles. The magnetic field lines do not intersect each other. Magnetic field due to a current carrying conductor. Take a long straight copper wire, 2 or 3 cells of 1.5 volts each and a plug key. Connect all of them in series. Place the straight wire parallel to over a compass needle. Plug the key in the circuit. Observe the direction of the deflection of north pole of the needle. You will observe that the current flows from north to the south, and the north pole of the compass needle would move towards the east. Now change the terminal of the battery, that is, positive to negative and vice versa. Observe the change in the direction of deflection of the needle. You will see that now the needle moves in the opposite direction, that is, towards the west. From this activity it is concluded that the direction of magnetic field produced by the electric current is also reversed. Magnetic field due to a current through a straight conductor. Set up the apparatus as shown here. Sprinkle some iron fillings uniformly on the cardboard. Keep the variable of the rheostat at a fixed position and note the current through the ammeter. Close the key so that a current flows through the wire. Ensure that the copper wire placed between the points X and Y remains vertically straight, and observe the pattern of the iron fillings. You would find that iron fillings align themselves, showing a pattern of concentric circles around the copper wire. What do these concentric circles represent? they represent the magnetic field lines. How can the direction of magnetic field be found? Place a compass at a point, say P, over a circle. Observe the direction of the needle. The direction of the current is from north to south. The deflection of the magnetic needle is towards the east. The direction of the current is from south to north. The deflection of the needle is towards the west. In this activity, we find that the deflection in the needle also changes. In fact, if the current is increased, the deflection also increases. It indicates the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. Now, place the compass at a farther point from the conducting wire. You can see the deflection in the needle decreases. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. Right-hand thumb rule. The direction of the magnetic field around a conductor is given by the right-hand thumb rule. It states that if a current-carrying conductor is held in the right hand such that thumb points in the direction of current, then the fingers wrapped around the conductor shows the direction of the magnetic field. This rule is also called Maxwell's corkscrew rule. If we consider ourselves driving a corkscrew in the direction of the current, then the direction of the corkscrew is the direction of the magnetic field. Magnetic field due to a current through a circular loop. Take a rectangular cardboard having two holes. Insert a circular coil having a large number of turns through them normal to the plane of the cardboard. Connect the ends of the coil in series with a battery, a key and a rheostat as shown here. Sprinkle iron fillings uniformly on the cardboard. Plug the key. Tap the cardboard gently a few times. Note the pattern of the iron fillings that emerges on the cardboard. When current is passed through a circular conductor or loop, the magnetic field is produced in the form of concentric circles around the conductor. Towards the center, the arcs of the circles become larger and appear as a straight line. Magnetic field due to a current in a solenoid. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. A solenoid SN whose ends is connected to a battery through a switch. When a current is passed through a solenoid, it produces a magnetic field around it. It is along the axis of the solenoid and is almost constant in magnitude and direction. The magnetic lines of the force inside the solenoid are nearly parallel to each other and parallel to the axis of the solenoid. A solenoid, when suspended freely, aligns itself in the north-south direction, thus behave like a bar magnet. One end of the solenoid acts like the North Pole and the other like the South Pole. The larger are the number of turns, the greater is the magnetism. The strength of the current. When current increases, magnetism also increases. Nature of core material used in the solenoid. If we use soft iron as a core for the solenoid, then it produces the strongest magnetism. Force on a current-carrying conductor in a magnetic field. A.M. Ampere suggested that if a current-carrying conductor produces a magnetic field and exerts a force on a magnet, then a magnet should also exert a force on the current-carrying conductor. Let us do an activity. Take a small aluminium rod AB of about 5 cm. Using two connecting wires, suspend it from a stand. Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards as shown here. Connect the aluminium rod in series with a battery, a key and a rheostat. Now pass a current through the aluminium rod from end B to end A and observe. you will observe that the rod is displaced towards the left. If the direction of current is reversed, the direction of displacement is also reversed. It is now towards the right. From this activity we can say that the force exerted is maximum if the conductor is perpendicular to the magnetic field in a current carrying conductor. According to this rule, stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular. If the first finger points in the direction of magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor. Fleming's right-hand rule. The direction of the induced current is given by the Fleming's right-hand rule. It states that if the thumb, forefinger and middle finger of the right hand is held perpendicular to each other such that the thumb points in the direction of motion of the conductor, the forefinger points in the direction of the magnetic field, then the middle finger shows the direction of the induced current. Electric motor. An electric motor is a rotating device that converts the electrical energy to the mechanical energy. The electrical motor works on the principle of right-hand thumb rule and Fleming's left-hand rule. An electric motor consists of a rectangular coil ABCD of insulated copper wire. It is called armature. The coil is placed between the two poles of a magnetic field such that the arm AB and CD are perpendicular to the direction of magnetic field. The ends of the coil are connected to two halves P and Q of a split ring called split ring commutator. The inner sides of these halves are insulated and attached to an axle. The external conducting edges of P and Q touch the two conducting stationary brushes X and Y respectively. These brushes are connected to the electrical circuit. Current in the coil ABCD enters from the source battery through the conducting brush X and flows back to the battery through the brush Y. Notice that the current in the arm AB of the coil flows from A to B. In the arm CD, it flows from C to D, that is, opposite to the direction of current through the arm AB. On applying Fleming's left-hand rule for the direction of force on a current-carrying conductor in a magnetic field, we find that the force acting on the arm AB pushes it downwards, while the force acting on the arm CD pushes it upwards. Thus the coil and the axle O, mounted free to turn about an axis, rotate anti-clockwise. At half rotation, Q makes contact with the brush X and P with the brush Y. Therefore, the current in the coil gets reversed and flows along the path DCBA. The reversal of the current also reverses the direction of force acting on the two arms AB and CD. Thus, the arm AB of the coil that was earlier pushed down is now pushed up, and the arm CD, previously pushed up, is now pushed down. Therefore, the coil and the axle rotate half a turn more in the same direction. If the coil is made to rotate continuously, it converts the electrical energy to mechanical energy. If the arrangement uses a DC, it is called a DC motor, and if the arrangement uses an AC, it is called an AC motor. Electromagnetic induction. In 1831, Michael Faraday proved that a magnet can create a current. The motion of a magnet with respect to a coil or a change in the magnetic field induces a potential difference in the coil and produces an induced current. This is called electromagnetic induction. Let us perform the following activity. Motion of a magnet with respect to a coil produces induced current. Take a coil of wire AB having a large number of turns. Connect the ends of the coil to a galvanometer as shown. Take a strong bar magnet and move its north pole towards the end B of the coil. There is a momentary deflection in the needle of the galvanometer, say to the right. This indicates the presence of a current in the coil AB. The deflection becomes zero the moment the motion of the magnet stops. Now, draw the north pole of the magnet away from the coil. Now the galvanometer is deflected towards the left, showing that the current is now set up in the direction opposite to the first. Place the magnet stationary at a point near to the coil, keeping its north pole towards the end B of the coil. We see that the galvanometer needle deflects towards the right when the coil is moved towards the north pole of the magnet. Similarly, the needle moves towards the left when the coil is moved away. When the coil is kept stationary with respect to the magnet, the deflection of the galvanometer drops to zero. Moving a magnet towards the coil sets up a current in the coil circuit as indicated by the deflection in the galvanometer needle. A galvanometer is an instrument that can detect the presence of a current in a circuit. The pointer remains at zero or the center of the scale for zero current flowing through it. From this activity we can state that the deflection in the galvanometer indicated that a current is induced in the coil. Let us perform another activity. Change in magnetic field produces induced current. Take two different coils of copper wire having large number of turns, say 1000 and 100 turns respectively. Insert them over a non-conducting cylindrical roll as shown here. Connect the coil 1 having larger number of turns in series with a battery and a plug key. Also connect the other coil 2 with the galvanometer as shown. Plug in the key. Observe the galvanometer. Is there a deflection in its needle? You will observe that the needle of the galvanometer instantly jumps to one side and just then quickly returns to zero, indicating a momentary current in coil 2. Disconnect coil 1 from the battery. You will observe that the needle momentarily moves but to the opposite side. It means that now the current flows in the opposite direction in coil 2. From these observations we can conclude that current is induced due to the change in the magnetic field. This process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. Electric generator. An electrical generator is a device that transforms the mechanical energy into the electrical energy. The working AC generator or dynamo is based on the electromagnetic induction. The direction of the induced current is given by the Fleming's right-hand rule and Lenz's law. An electric generator consists of a rotating rectangular coil ABCD of insulated copper wire that is called an armature. It is placed between the two poles of a permanent magnet. The two ends of this coil are connected to the two rings R1 and R2. The inside of these rings are made insulated. The two conducting stationary brushes B1 and B2 are kept pressed separately on the rings R1 and R2 respectively. The two rings R1 and R2 are internally attached to an axle. The axle may be mechanically rotated from outside to rotate the coil inside the magnetic field. Outer ends of the two brushes are connected to the galvanometer to show the flow of current in the given external circuit. When the coil rotates clockwise, AB moves inwards and CD moves outwards. According to the Fleming's right-hand rule, the current induced in AB is from A to B and in CD from C to D. In the external circuit, current flows from B2 to B1. After half of the rotation of the coil, AB is at the back and CD is at the front. Therefore, AB starts moving outwards and CD inwards. The current induced in AB is from B to A and in CD from D to C. The current flows from B1 to B2 through the external circuit. We therefore see that the induced current in the external circuit changes direction after every half rotation of the coil and hence is alternating in nature. To get a direct current DC which does not change its direction with time, a split ring type commutator must be used. With this arrangement, one brush is all the time in contact with the arm moving up in the field, while the other is in the contact with the arm moving down. A unidirectional current is produced when the coil rotates between the magnetic poles. The deflection of the galvanometer needle shows that the current is induced.